In this third part of the 1.9 lesson, we're going to define two very important properties of linear transformations, and then we're going to apply them in a couple exercises. The discussion is a little bit complicated at the beginning, maybe, and I think you'll see once we get to the exercises, it's not so bad, but these are really crucial concepts, so we are going to take a little bit of time to talk about them. A transformation T from Rn to Rm is said to be onto if every vector in Rm is the image of a vector in Rn. In other words, if the range of T equals all of Rm, or using some of our other language, the range equals the codomain. The reason we use the word onto is the idea is that the images of this transformation cover the entire codomain space Rm. So it's onto the whole thing. There's no vector that's missed as an image. Let's look at an example. Here's a transformation from R3 to R2 defined by T of x equals Ax, where A is this matrix. Notice that's a 2 by 3 matrix, right? We want to show that T is onto. Now we'll have an easier way of doing this eventually, but see if you can follow this argument, these arguments that I go through. To show that T is onto is I'm going to pick any vector in R2. I call it AB. It's a vector in the codomain space. I want to pick any vector at all in R2, and we need to find a vector x in the domain space, so it has three components, it's in R3, such that T of x equals AB. Now, we can write down what T of x does, because we have the matrix A, right? T of x is the matrix A times the vector x, and here I write out what we end up with from this matrix is just x1, x2. It takes the first component of x, the second component of x, and just leaves it as a two-component vector. So if T of x is equal to AB, that means x1, x2 has to equal AB, and that means x1 has to equal A, x2 has to equal B, x3 could be anything. So what I can do is I'm just going to pick x3 to be 1,000 just to be different. And I can actually say, okay, we started with a vector AB. Now I'm going to take AB 1000 as a vector in R3, and the image of AB 1000 is AB. So we have found our x. And we have shown that the linear transformation T is onto R2. Now here's another example. This is a linear transformation from R2 to R4, defined by matrix multiplication, where A is this matrix, so it's a 4 by 2 matrix. I want to show that T is not onto here, not onto. So again, I can actually compute what T of x does. Here the domain consists of our two vectors, right? So when I multiply this out, I get this vector in R4 in the codomain, x1, x2, 0, x1 plus x2. And that's the key to see what's going on here, because I observe all image vectors have a 0 here in the third component. So any vector in R4 that has a third entry that is not 0 will not be in the image. So for example, 1, 2, 3, 3 is not an image of any vector in R2, and we have shown that T is not onto. Okay, now we're going to define another concept different from onto. Transformation T from Rn to Rm is said to be one-to-one if any vector in Rm is the image of at most one, maybe none, vector in Rn. If you've ever heard of the concept of one-to-one function, this matches the concept of one-to-one function. You cannot have with a one-to-one transformation, you cannot have two different vectors in the domain that map to the same image, that have the same image. So I want to go back to my earlier examples. So I labeled them A and B at the beginning. So go back to the first example that we used in ONTO. Is that transformation one-to-one? Now we already know that that transformation took x1, x2, x3 and mapped it to the image x1, x2. So we know x3 does not affect the image. That's sort of the key observation. So if I pick two different vectors with the same first two entries, but different third entries, let's look at what happens. Well, t of 1, 2, 500 is going to be 1, 2. And t of 1, 2, negative 60 is going to be 1, 2. So 1, 2 is the image of more than one vector, so t is not one-to-one. Let's look at the second example from before. Is that transformation one-to-one? Now, how would you show that it's one-to-one? What you would have to do is you'd have to say, well, suppose x and y are vectors in R2, so in the domain of this transformation, such that t of x equals t of y. Now remember, this was the second example of ONTO, right? So if t of x equals t of y, here's the image of x, here's the image of y. If vectors are equal, their corresponding entries must be equal. So it would have to be true that x1 equals y1 and x2 equals y2 in particular. But those vectors started out as being just x1, x2, y1, y2. And if x1 and y1, x2, and y2 are equal, then those two vectors have to be equal. So in other words, there's no way for x and y to be different in this situation. There's no way for two different vectors, x and y, to end up with t of x equals t of y. This means that any one vector in R4 can be the image of at most one vector in R2. Therefore, the transformation in that example is one-to-one. Now, I'm not going to ask you to reproduce this kind of argument, so I'm not going to dwell on it. We're just going to move on and try to get to some exercises here, and I'll be clear about what I really expect you to do. But I still think it's interesting to think how you would show a transformation is ONTO or is not ONTO, and how you would show a transformation is one-to-one or is not one-to-one. Right, now we're going to move on to a theorem related to one-to-oneness. A linear transformation T is one-to-one if and only if T of x equals 0 is true only for one vector x, namely x equals 0. What this theorem is saying is for a linear transformation, if you know the transformation is one-to-one at 0, it's one-to-one everywhere. Like you really only have to verify that it's one-to-one at 0, then it's one-to-one everywhere. And I actually want to talk through the proof of this a little bit with you because I think it's very accessible. When we say if and only if, we got two directions to show, two implications. So first assume that T is one-to-one. Suppose we know the transformation is one-to-one. We want to show then that T of x equals 0 only for x equals 0. So for any linear transformation, we know T of 0 is 0. That's always true. Since T is one-to-one, there cannot be a different x different from 0 such that T of x equals 0. So we got the implication in one direction. Now we want to show the reverse. We want to say if we assume T of x equals 0 only for x equals 0, we want to show this implies that the transformation must be one-to-one. So assume T of x equals 0 for only x equals 0. We want to show T is one-to-one. Suppose we have u and v such that T of u equals T of v. Again, but we were going to end up showing that u must equal v, but let's see why. T of u equals T of v. Well then, T of u minus T of v must be 0. By properties of linear transformations, that's the same as T of u minus v. So T of u minus v, which is T of u minus T of v, is 0. But we've just said, the only vector whose image is 0, so u minus v itself must be 0, so u equals v. So this means that T must be 1 to 1. Theorem 12, we're going to apply in an exercise, and as soon as we read the theorem. Theorem 12, suppose T from Rn to Rm is a linear transformation with standard matrix A, then T is onto if and only if the columns of A span Rm. That is, if and only if every row of A has a pivot position. So what we're doing is we're turning this abstract concept of onto into an equivalent statement about the matrix of the transformation. So it's only if A has a pivot position in every row. Part B, T is 1 to 1 if and only if the columns of A are linearly independent. This theorem gives us an easier way to check whether a linear transformation is onto or 1 to 1, at least if we have its standard matrix. And I think what I want to do is we're going to do these exercises in then another segment. So I'm going to cut it off here, and then we'll do the exercises.